This is the fifth session in Climate Change and Where We Are. In these sessions, we try to look at the challenges of the climate and biodiversity crisis and just how short time is and how difficult it is, but also we look at some of the more ambitious solutions. One of the key solutions could be biochar. This is essentially a type of charcoal, or many types of charcoal, that you can produce from different feedstocks. So building wastes like wood from building, stubble from agricultural waste, or seaweeds. All of these things can be turned into different qualities of charcoal and can be used for different purposes. There's applications to help make agricultural land need less fertiliser and more resistant to drought. And the charcoal or the biochars can also be used as filters, and there's a whole other range of uses. We were lucky enough to be joined by Saran Sohi, Ondřej Mašek and Stuart Hazeldean from the University of Edinburgh and also the UK Biochar Research Centre. They took questions for us, and also Stuart did a presentation at the beginning. We did have some technical issues at the beginning of the presentation where we weren't live streaming over YouTube. We were over Zoom, but not YouTube, so no one could see what was happening. Stuart very kindly offered to do his presentation in full, so we actually have a longer version and a more complete version of the presentation that he condensed at the beginning of this session. And we have edited that in to the beginning of this session, so it's actually a more complete session. And luckily Ondřej and Saran offered to stay on for longer to allow us to answer as many questions as we could from the community, and we had some excellent questions from the community. So it's a really interesting session and one well worth listening to if you are interested in biochar, and I certainly am. And I'll just leave it there and pass over to Stuart's now extended bonus presentation that we were lucky enough to get off the back of technical hitches that we were unfortunate enough to have in the first instance.
Hello and welcome. This is a recording of the seminar presented to the CFCA on the 14th of July 2021. And I'm going to talk about biochar. My name is Stuart Hazeldean. I'm a professor of carbon capture and storage at the University of Edinburgh in Scotland. And about 10 years ago, probably more, we set up the Biochar Research Centre, which still exists at the University of Edinburgh, recognising that biochar looks very likely to have a useful and important role in mitigating and trapping carbon for climate purposes, and also to improve and enhance soil quality and the uses of that soil for growing valuable crops. So I'm going to start sharing my screen. And on the first slide, we see here a picture of the central part of the University of Edinburgh. And this old building is a Georgian sandstone building. And the purpose of showing you this in the centre of Edinburgh is on the northwest corner up here. Used to be a chemical laboratory in the 1760s, and in that department of chemistry, that's where Joseph Black first isolated carbon dioxide and named that carbon dioxide as fixed air. And you can still see some of the glassware from that time. The chemical glassware is archived in the Royal Scottish Museum immediately adjacent to this old college building of University of Edinburgh. So here we discovered fixed air carbon dioxide, so we can claim that merit, but of course not get involved in any of the liabilities attached to carbon dioxide. So I'll now outline what is biochar, how that fits into the climate conundrum, and how that fits into some of the things you can do with biochar. And the general purpose of this entire type of conversation is predicated upon the undoubted, very strong evidence that the climate now is systematically changing and changing very quickly, exactly as predicted by climate models, because of the increasing carbon dioxide emissions here shown in thousands of millions of tons or billions of tons a year, 45 billion tons a year emitted now, are plotted against time, human time from the very recent 1980s through to 2050, the proposed net zero date of the UK, through until 2100, by which time the world should be achieving net zero. And what this graph shows is the history of carbon dioxide emissions on the black line, The red line, which we're still on, which is the emissions if we fail to do anything as a species and a political coordination around the world. Here is the predicted increase in temperature by ever increasing quantities of CO2 being placed into the atmosphere by ever increasing quantities of fossil carbon being extracted out of the ground and present day biomass carbon being burned. And what this red line shows is a 50% probability of a 5-degree warming, with a 10% probability of an 8-degree warming and a 10% probability of a mere 2.5 or 3 degrees of warming. Any of those are entirely out with our experience as a species. During the past 10,000 years, one of the reasons for the success of our species has been the relatively stable and relatively unchanging temperate climate in an interglacial period. Where we want to be is on that blue line, decreasing emissions through time to get to a balance between emissions and storage, and then moving down to a net zero where we store more carbon than we actually produce. And to do that, we need to do three types of things. We need to become more efficient in the way we use energy. So to get the same performance value out of the energy, but no extra emissions. So a simple example would be putting 4 people in a car instead of 1 person. That effectively uses only a quarter of the emissions for that journey. We also need to move to near zero carbon methods of generating energy. And that is where renewable energies come in, whether that's onshore wind, offshore wind, solar panels, tidal power, gradually and progressively replacing coal-fueled electricity generation, which we've largely replaced in Europe now, and put in its place a transition to methane gas-fueled electricity, which is about half the carbon emission for the same unit of electricity, but still a high carbon source gas-fueled power. And we need to move to a net zero electrical embedded carbon in that electrical system. And to help us do that, we also need to switch fuels from methane gas, from coal, into using the same fuels, but taking the carbon away by trapping carbon after the fossil fuels combusted through carbon capture and storage, or chemically splitting methane gas, CH4, into hydrogen plus carbon dioxide, where we can store the CO2. So we're progressively switching into fuels which have less and less carbon in them, from coal to oil to methane and then to hydrogen. And of course, to do that, we also need to store huge quantities of carbon dioxide, billions of tons per year of carbon dioxide. And these are immensely big numbers. And what we'll see is that many of the activities proposed are too small on their own. So we need to do multiple activities, lots of different things, all the things we can think of to reduce our carbon emissions as soon as possible, to get down from that red line past the pledges of the 2016 Paris Agreement down to pledges of the 2021 Glasgow Agreement, hopefully, which is much closer to that 2-degree sustainability line. And lastly, on this graph, past the point of balance, we need to achieve an overall net negative. We need to be pulling carbon out of the air and storing more carbon than we're producing. So we're effectively recapturing and removing carbon from air. And so biochar can fit into 2 of these boxes about fuel switching and storing CO2, and biochar also enables carbon dioxide to be removed from the air by trees, crops, vegetation, and that biochar can then store that carbon, or some of that carbon, back underground where it does not go back into the atmosphere. So there are 2 types of end member consideration here, opposite extremes, if you like. Firstly, on the left is the very straightforward and perhaps easier to understand methods of storing extra carbon stock, taking carbon out of the atmosphere and stocking that in a temporary archive. And that archive might be a forest here with lots of, in this case, lots of hardwood and broadleaf trees. That carbon archive and store might be hedges, as this part of Normandy shows. Then hedges used to be a lot more common before we had big, large-scale farming developed in the UK. So the carbon wood in a hedge stores fossil carbon for a few decades. And of course, You can look after the land and tend the land, both for arable crops or for livestock, or rewilding the land to store more carbon into that productive flat land. So this type of thing is pretty familiar to many people in the public. It fits with your common everyday experience of understanding what trees are, of understanding what hedges are, of understanding what farms and land use are. So this is, of course, extremely popular. But as I'll try and show you in a minute, this only increases the stock of carbon on the surface of the Earth. None of this actually stores carbon for long periods of time, because we need to store carbon to let the climate readjust. We need to store the carbon for something like 10,000 years, not just 10 or 20 years for hedges, or a few decades, or 100 years or 200 years for trees, but we need to store carbon for very long periods of time on a human timescale. But the good news is we know we can do this, because here is a carbon store on a geological timescale. These are the White Cliffs of Dover, and the White Cliffs of Dover are made out of chalk. And chalk, of course, is the mineral calcium carbonate, very small particles of carbonate algae grown in the sea about 120 million years ago. And those carbonate particles sunk down to the bottom of the sea, carrying the carbon from the seawater with them, and have stored the carbon from seawater in those minerals ever since. So that has been safely and securely stored for tens and even hundreds of millions of years, much, much longer than the 10,000 years we need to store carbon right now to let the climate readjust. So there is an option of short duration storage, easy to understand, longer duration storage, slightly more difficult to engineer, perhaps a little bit more difficult to understand. But should we think of these in the same way, or should we value them differently? And I'll argue that short duration storage is good. Long duration storage is the ultimate correct standard, and actually biochar lies somewhere in between. Biochar has attributes of both, and I'll try and show you that on this graph here. And this graph shows you the total quantity of carbon dioxide emitted through time. And here's a human type of time scale: 100 years, 1,000 years, 2,000 years, 10,000 years. So right now, as humans, we're busy digging up as much coal and as much oil and as much gas as we can dig up to have the energy to support our lifestyles. And we're also still burning off very large quantities of forest, whether that's accidentally in China or California, in Canada, or the Arctic Russia, or in California, or is semi-deliberately in the rainforests of Brazil. Large amounts of biomass are going up into the atmosphere. So here we can see that carbon goes into the atmosphere very quickly, but then it's taken up by natural processes very, very slowly. So initially, carbon dioxide in the atmosphere dissolves in seawater, and a lot of that carbon dioxide can dissolve over a few hundred years in the seawater, but that does not get the excess carbon back down towards zero. That carbon dioxide is still in excess in the atmosphere and driving global warming. The natural process of weathering carbonate rocks, of weathering limestone, weathering statues, weathering building stone occurs. That takes carbon dioxide out of the atmosphere by reacting with acid rain. That takes carbon dioxide out of the atmosphere over periods of several hundreds or a few thousand years. Silicate rock weathering, when we're weathering granites, we're weathering basalts, we're weathering reactive minerals in volcanic and igneous rocks, much more so than in sandstones. Those silicate rock weathering reactions are slower and occur over several thousand years, but will bring that carbon dioxide level down. And those three processes and other interventions by nature will gradually bring carbon dioxide back towards where we started off, but still, even at 10,000 years, not back to the same level. So my point here is that CO2, natural decreases of CO2 in the atmosphere, are actually quite slow on a human timescale. So the value of trees capturing and stocking carbon for a few decades is quite small. The value of geology, of chalk storing carbon for a long time, is quite large. And to show you what I mean here, if we stored our carbon dioxide geologically in the chalk by making that mineral in the surface of the ocean, then we can do that once. We do that 120 million years ago in the Cretaceous chalk, and that carbon has been stored uniformly without any care and maintenance right through past 10,000 years, right up to the present day. By contrast, if we grow trees or a forestry, or if we go hedges, that's actually a short cycle of carbon stocking, putting the carbon from the atmosphere into that wood or into that soil. But when the wood dies, then after a few decades or 100 years or 200 years, that carbon is inevitably released back into the atmosphere. So to carry on, to have the same long duration effect of carbon in the atmosphere, we need to repeat that cycle of tree plantation and tree growth again and again and again, and perhaps 100 times into the future. So for maybe 100 or several hundred generations into the future, we need to guarantee that we're going to keep on replanting and increasing our forest area. And that's a pretty difficult guarantee. I don't know anywhere in the world where that guarantee can be made. And of course, biochar then lives somewhere in between. Biochar is well known archaeologically to last for decades in the soil. Many places in Europe for hundreds of years in the soil, we can find archaeological charcoal, and some parts of the Brazilian Amazon, very famously on the Terra Preta soils, we can find rich deposits of charcoal which look as though they're thousands of years old in those tropical soils. So biochar can have the merits of being a biomass, and easy to understand and acceptable action, with some of the benefits of the long duration storage by putting carbon back into the ground. And so that's why it's attractive. It has merits of both of these. And to just illustrate that point, again, it's very popular at the moment to think about and to act on planting trees. And I'm all in favor of planting trees. That will definitely draw carbon out of the atmosphere. But we have to realize that the amount of carbon, those very big numbers I talked about, those 40 billion tons a year, that is vastly greater than the amount of forest available or the amount of forest land we could make available, because every European effectively needs about 3 football pitches operating as forest throughout their lifetime to capture and stock the carbon which they've pulled out of the ground and have emitted into the atmosphere. That carbon in 3 football pitches will store the carbon from my lifetime, or rather it will stock it, but it won't store it for very long. After the trees die, then that carbon goes back into the atmosphere. And we also know that there are big natural hazards with trying to store carbon in forestry. So here's some of the bark beetle epidemic in Canada and in Northern California, where huge areas of natural forest are just left standing as dead wood after infestation by the bark beetle. And of course, we're all familiar with the pictures of forest fire in Canada or in Siberia or in California, and now increasingly so in parts of Europe and even the UK. So forest is good, but it's not secure for the long period of time. So let's think about biochar. And the important thing to realize that what I'm talking about here is biochar not as just the residue of charcoal after not burning the fire properly. This is biochar as a deliberately constructed, well controlled and understood feedstock into a very well engineered kiln or a furnace, which has its airflow controlled, so we can control the temperature, we can control the airflow, we can control the time duration of making biochar. So we can specify and tailor and engineer the biochar we make and accommodate different feedstocks by having slightly different process settings to make biochar. And one of the uses of biochar then can be that we can turn biochar into pellets for easier handling. So it's not just lumps of wood, it's not just dust. Here we can make pellets, and we can also make small-sized pellets for horticulture or agriculture. Here is biochar for sale in a garden centre, for example. And by doing this, we also know that we can add components into that biochar. We can add rock dust, crushed up, powdered basalt, natural basalt rock or dolerite rock, because that basalt or dolerite rock carries minerals, potassium, sodium, phosphorus, and combined with nitrogen, where we can make this biochar function as a carrier of a slow release fertilizer. So we can engineer this biochar to have soil benefits and also transport nutrient benefits where we put it. So we can engineer the types of biochar we have. Here's an example of some biochar experiments with a Chinese group with biochar at 400 centigrade, 450, up to 600 centigrade. And you can see that the amount of hydrogen decreases and the amount of oxygen decreases. It's getting more and more baked and driving off those volatile hydrogen and oxygen, some of the carbon. So we can control and engineer that. And we can see what happens to the microstructure of biochar as we increase in temperature. We lose the biological features of the biochar, and it becomes more and more homogeneous. And of course, if we just make our biochar very slowly at 400, 500 centigrade and delicately, we can preserve the three-dimensional internal structure of the biochar with lots of holes, lots of micro holes and porous space where nematodes and soil microscopic wildlife can live, where microbes and small-scale biota can live in these micron or 10 micron sized pores. And also, if we've combined that with a crushed mineral rock, then this crushed mineral is spread physically and pasted in through the biochar physically. So biochar is a deliberately engineered and complex substance, or it can and should be, because we now know from the best compilation of evidence done by establishment, totally impartial science examination by the Royal Society of London and the Royal Academy of Engineering. Their report on greenhouse gas removal looked at biochar, and they agreed that biochar does store carbon in the soil for long periods of time, for decades and decades. We do know that biochar can provide soil fertility improvements and soil quality improvements by holding moisture, by increasing the porosity of soil. In the UK, the soil fertility is often marginal. The increase in the tropics with depleted soil, the soil fertility benefits can be extreme, can be spectacular. Biochar was also acknowledged in this report to be a well-established method. We know how to make biochar, we know how to carry it, we know how to deploy it, we know how to measure it. And the main problems are not the science really, but the cost of making biochar, which is partly the cost of transporting the feedstock to the pyrolysis kiln unit, and the fact that it's difficult to buy the equipment, especially in the UK, where we know at the moment have no biochar supply chain. And there is great confusion about the correct application rates of biochar. Some people want to put as much as possible on the ground. Other people are targeting their biochar with maybe just 1 ton of pellets per hectare per year. Our work, of course, shows that targeting creates the best value, the best financial and soil value for that biochar. And there's been a lot of debate about whether biochar decomposes, how permanent that is. But again, Royal Society evidence was satisfied that biochar permanence is genuine, can last for many decades and many hundreds of years. And the amount of biochar, what impact can that have on carbon dioxide emissions every year? So globally, between 1.8 and 4.8 billion tons of CO2 per year. So in simple terms, at its best, that would be about 10% of global emissions could be turned into biochar and stored every year. So that's a pretty significant action, but on its own, not enough, but still a significant action. And a similar number for the UK, 6 through to 41 million tons per year. Again, about 10% of the UK's annual carbon dioxide emission. So again, on its own, not enough, but a very valuable part of a group of actions to reduce and store our greenhouse gas emissions. So significant, can be done, can be controlled. And there are 3 things we need to be aware of with biochar. Firstly, there's the feedstock. That needs to be guaranteed, secure, pure, uncontaminated. And when I say uncontaminated, I mean uncontaminated by industrial human activities. So there's no point in using old tires to make biochar because of the weird mix of cyclical hydrocarbon compounds you get out of pyrolyzing old tires. You can pyrolyze them, but it's a bad feedstock because it's got lots of toxic chemicals in. Whereas if you do control your feedstock, you can use annual crops such as straw, rice, or sugarcane. You can use crops which grow over a 10-year period, such as willow or maybe miscanthus. You can use feedstocks, avoid feedstocks which are contaminated, such as municipal waste or toxic filter residues, avoid plastics. And there's also inevitably some judgment about the contest between the land area being used and the regeneration required of that, and are we going to use that land area for food or not? So in terms of conversion of the feedstock into biochar, we know how to do pyrolysis. We build kilns which are partly or completely enclosed where we can control the airflow through. And so we can make biochar at rates of between 1 tonne and 100,000 tonnes a year at different facilities in the UK. We can be site specific on the kiln and tailor that kiln condition to the type of biochar. So if we've got a whole set of spruce wood coming in, then we'd have a type of kiln working for that. If we've got a set of straw and wheat chaff coming in, then we'd have a kiln geared up to tailored for that. Handling biochar, just like any biomass, of course, is volumetrically large. The handling needs to be efficient. And so in practical terms, thinking on the transport scale of 10, 20, 30, 40 kilometers only is what you want to be able to think about from source of biomass to a biochar pyrolysis facility. And of course, being efficient as part of the consequence of feeding the biomass through the kiln, we produce biochar, but we drive off the gas like methane gas and carbon monoxide, and we drive off the bio oils from that. Now, those can be sometimes collected and used for biological feedstock purposes to make chemicals, but those can also, at its simplest, those can be burned to provide heat. So those should not be wasted. Those should be burned and combusted to provide heat. So the pyrolysis equipment ideally should be plumbed in to something which needs heat, something like a greenhouse complex, a district heating scheme, a wood drying warehouse, for example. All of those need low-grade heat over long periods, and biochar heat can replace fossil fuel heating, can replace electric heating. Just combusting biochar in a pit made with where we've got a release of those gases and oils back to the atmosphere is a waste, and actually helps to increase global warming in many ways. So don't waste the emissions. Do make sure you have clean feedstock without contamination. And usually mobile biochar pyrolysis units are going to be less efficient. The key is to use the side products of that biochar. That's what makes it most efficient. Where can you use this? And the biochar can be used as a land additive. That's what most people will think of, but I want to make that more subtle to say we can tailor our biochar to be specifically active, but also to hold the specific minerals to act as a slow release targeted fertilizer. We know that works with improving our forestry take up of seedlings. We know that that improves the growth of trees, even in the UK over the first 5 years. We know that improves seed germination where we're dealing with arable crops. The main carbon use, of course, is for longevity of storage for tens and hundreds of years rather than just a few years. That can be in longevity of carbon. A biochar in the soil as its own substance can be placed into peat to store for even longer in hundreds of year duration or thousands of year duration peatlands. And we're experimenting with biochar as foundations in engineering infrastructure. So for constructing roads, railways, or airports, putting biochar in as a base layer can store carbon and offset the carbon due to that as a consequence of that construction. So again, none of these things on their own are enough, but combined together, they add up to a significant input. And the missing thing is the carbon market or the payment, like the ELMS system that's proposed in England. How will farmers or land tenants be paid or reimbursed at least partly for increasing the stock of carbon in the soil? And one part of that could be biochar. So we have to be aware and careful of overdosing. Don't overdose. It's not about turning the land black. It's about targeted, profitable use of biochar. There's an unsolved problem in how to measure the longevity of biochar. I mean, we can do that by taking soil samples and physically measuring that, but we need to develop much better sensors and drones and satellite measurements, which I think we can do. Beware of contamination. That's been a major block for regulators, the fear of contamination. But again, having reliable certification of your supply chain is very important. The source of your biomass is vital. And we need to fix that reliability and clear payment system. So the barriers to biochar, why hasn't it already happened? Well, because of the official regulatory and government reticence, there's been no payment system for biochar. So all the activities have been done really by enthusiasts or people trying to find niches for a biochar market. So consequently, there's no supply chain for biochar, which is easily accessible in the UK at the moment. And likewise, there's no supply chain of biochar kilns or apparatus for making biochar. So that niche has been filled by enthusiastic small startups or even amateurs with even simpler kilns. So here's one made by Carbon Gold for a farm scale kiln where you would put your biomass in at the top, try and combust that with reduced air supply, and the flue gas and the waste gases may go off the top, and when that's finished after 3 or 4 days of slow combustion, you would open that up and shovel out your biochar. But of course, that's not connected to a usage system for the valuable waste products. We're losing lots of heat through the sides. You know, this is a way of making biochar, but we can and should be doing a lot better. And equipment does exist in other countries, in France or in Germany, in India, in China. Biochar is being used, and in many countries in Africa, biochar is being used already on an agricultural and village and town scale. So skepticism by regulators, we think, can be overcome. We've got much better evidence. Soil fertility does improve soil fertility in the tropics in degraded soils, much less of an improvement in the UK. So the value in the UK is about having better ways of operating and about storing of carbon. We need to have the limit on biochar use is controlled by the amount of feedstock. And we haven't really thought seriously enough about the total amount of feedstock which could feed into biochar, but there's nothing to stop us starting. We can start biochar tomorrow if we want to. One of the main issues, though, in the competitive carbon marketplace is that biochar can save money if you divert pure green waste from going to landfill. You save the gate fees on the landfill, so turning that waste into biochar can be a saving, i.e. a negative price. But usually, then we're going to have to pay to charcoal and pyrolyze that biomass. And so biochar can come in at a price anywhere between 15 and 140 pounds a tonne. Now, that's not a terminal problem, that's just what the price is, and that is well within the range that carbon prices are creeping up to now. Carbon prices are already ahead of that in parts of UK industrial activity, and carbon prices will undoubtedly get to this level. And so, but we need to find a way of transmitting the carbon price to pay for the biochar. But I'm optimistic because right at the moment, there are 4 commercial projects being funded by the Department of Energy, by BEIS, working on biochar deployment in farms of different types, and even through to putting biochar in peatlands and biochar in and decreased gas emissions during glass making. That's what I was trying to say. So 4 projects there already underway for a year or so. Some will go through further and others will collapse. But again, we've got a chance of making this commercial now. And as part of the Biology Research Council and the Natural Environment Research Council has created a greenhouse gas hub, and that has 5 trials of nature-based solutions going on about how to absorb carbon from the atmosphere using natural plant and natural processes. And in all those 5 trials, the guiding science wants to use some biochar in each of those. And the last couple of slides, what do we not know? We don't know how to monitor the soil carbon properly, how biochar increases the soil carbon. As I said, we can do that manually, but we need to automate that. We need to build better models, computer models, to predict that, which the models can predict, to just use the sampling as confirmation of the prediction. Automating this with large data sets is clearly a best way to go if we can. Biochar also decreases the greenhouse gas of nitrous oxides running off and decreases the nitrate contamination of groundwater and of river courses. So there's another side benefit. We can and have done added rock dust as a slow release fertiliser to pellets, so that can save an individual farm tens of thousands of pounds a year in buying fertiliser. And we can measure the effects of biochar at a small scale within the field, and we can also measure the effects of that change of fertility through whole river catchments. And what we need to do now is work on the creation of these integrated systems where we're growing the feedstock of biomass locally, we're gathering it locally, we're taking it to a pyrolyzer 10, 20, 40 kilometers away maybe as a cooperative system. That's plumbed in to use the heat and the oil to supply biomass products or heat energy to local users, and what makes biochar, which we've got an authentic supply chain guarantee, and we can use that in highly tailored applications which have good value, right from growing additional more efficient sprouting of grain through to better trees growing faster, through to removing the carbon dioxide emissions from the burps of sheep and cows and making meat production less CO2 intensive. And so what I've said is biochar is widely recognized as beneficial. It requires a valid biomass feedstock, which is pure and guaranteed. We're on the cusp of starting to develop that commercially now in the UK. This can be a real thing. Some of these projects can be commercial within 3 years now, I think. We've had numerous field trials of biochar in the UK over the past 15 and 20 years. We've got more analyses than we need to understand how biochar works. And we believe from that the application of biochar is secure, and we believe that the regulators can and should have confidence and can and should be able to develop a market model by which biochar can become business as usual. And so thank you. That's all I want to say on that, and I'll stop sharing, and I will also now stop recording. So my name's Stuart Hazeldean, University of Edinburgh School of Geosciences, and thank you for listening.
Yeah, so Saran Sohi, School of Geosciences. I'm a senior lecturer. My research as an environmental scientist working mainly with soils has been around the value of organic matter in soil, which leads to the storage of carbon. And then I got very interested in biochar, which is a very distinct and important possibility, I think, in terms of getting soils to work better and also store more carbon.
Okay, my name is Ondřej Mašek, also from the School of Geosciences. I'm a reader in engineering systems, and my background is really engineering technologies for conversion of biomass. And for the past 12 years or so, I've been focused on conversion of biomass with the aim to store carbon. So in this case, to convert to biochar from diverse feedstock and to provide biochar that's suitable for different applications. So Stuart introduced soil applications, but there are a number of other potential applications for biochar. So it's really my focus is on how do we match feedstock, the conversion process, and the final application.
And I'm Stuart Hazeldean, also from the University of Edinburgh in the School of Geosciences. I'm originally a geologist, not a soil scientist, but I'm interested in biochar and working biochar on the edges because it's part of the portfolio of carbon storage technologies and actions which we need to do as a species to try and decrease our emissions to atmosphere and try and recover back from the atmosphere some of that which we've already emitted.
Thanks very much. I'll just hand over to you, Daniel, and if you can just go through the questions as is. I think they're looking pretty discreet. So yeah, just take it away.
Okay, so I'm going to read out some of the questions that we've had submitted on our Slido. The first one that has a few upvotes is, if it's used on land, does it degrade or run off and then go into rivers? Is there any work on the effects of this?
So it sounds like a Saran question to me.
Yeah, So we know that from natural systems where fire is a more frequent occurrence. So forest systems that burn frequently. So this is around the world. So we know quite a lot about the longevity of the charcoal that is produced, and which is a very small portion of what burns. But we know about its longevity, and from that we can infer, I think, the longevity of biochar. And generally, biochar that's made for carbon storage will be more stable because, well, through Ondřej's work, really, we know about the conditions that create the most stable forms of biochar. But yes, slowly it does degrade. So it's not the same as geological carbon storage. In terms of where it goes, the soil is very effective at creating structure, which then protects things that would move through soil. So soluble things move more readily in soil water. And the ash that you might get when you burn something is likely to be present inside biochar. That does leach out slowly, and that has a nutrient value. And in small quantities, that's beneficial. I suppose if you add very large amounts of biochar, which I think is quite improbable, actually, high doses. When I say high doses, some of these experimental doses of multiple tens of tons per hectare, then you might get a flush of these nutrients from that source. In terms of the solid material, there's some limited movement, but really the minerals in the soil rapidly interact with biochar, create coatings, and biochar becomes incorporated into the soil structure in the same way as organic matter from plant material. So, it really doesn't seem to move through the soil vertically or horizontally, as far as some people might sort of imagine.
Just quickly, in terms of processing it to get it into the soil, do you have to break it down to really fine dust at all, or is it the biodiversity manages to find its way through the whole structure?
Yeah, we've had a lot of
pieces.
Yeah, I think we've had debate about this. I think depending on what you want to apply with the biochar and integrate into the product, you might form it in different ways. The advantage of creating pellets is that they're very easy to handle and apply, and they are more dense in terms of moving things around, in terms of putting them through farm machinery, in terms of integrating nutrients that you might want to co-apply with biochar. It becomes much easier if it's in a formulated pellet. Then you lose some of the, if you like, the native structure of the biomass that it came from, but you still have the porosity and absorptive properties of the surfaces that are created in the process of pyrolysis. So again, it's this interface between the work that I do and the work that Ondřej does. So yeah, I think we understand a lot of that now, and I think we're working with specific applications to think about the optimum mode of use. But I think generally things that are easier to handle are more predictable. If they fall apart in the soil, which is really what is likely to happen, that's not really a bad thing. It distributes the impact of the material more widely.
Thank you.
Okay, I'll move on to another question. Can the oils that are produced also be used in bioplastic manufacture?
Okay, that's a good question. The liquid products that can be collected from pyrolysis, they contain hundreds of different compounds. And so the challenge there is really separating those that you want to use for bioplastics or for various other things. So there are organic acids and a number of other chemicals that can be of quite a high value. The challenge is to get them out in the right concentration and the right purity of the product. So the simple answer is yes, you can do a lot of things. You can do bioplastics, you can do other things, but this will depend also on the scale. So all these will require dedicated chemical processes. So this is more suitable for medium to larger scale facilities, not necessarily something you want to be doing or you could be doing on a farm scale. But yes, in theory, you can do that. There are a lot of compounds of interest that can be used for the material production.
Thank you. So we have a question that was actually posed by Ian himself as well. So it's about kelp, how it represents possibly the biggest source of cellulose with many associated benefits. What grade of biochar can be created from seaweeds?
Okay, I'll take that one to start with. So yes, biochar can be produced from seaweed. We've done that. We have a number of samples in the archive that Stuart mentioned, both from seaweed and also from microalgae. So we can use all types of algae for that. It's a very different type of biochar, both in terms of structure and the composition, because of the difference in the composition of the feedstock itself. So being almost with no lignin in it, the yield of biochar tends to be lower, at least the yield of carbon, because most of the material turns into volatile, so again, the liquids and the gases that can be used for other applications. But it also tends to be rich in minerals that are present in the algae itself. So depending on where the seaweed comes from, it can contain sometimes high concentrations of heavy metals. Again, very much depending on where it is coming from, what environment it was produced in. And also the structure, it doesn't have the sort of porosity that you could see on Stuart's slide with the electron microscope image. It looks very different. There tends to be more sort of like sheets of carbon that are layered on top of each other. But if you want to use larger particles, then that has an impact on that. So just to answer the question, yes, it's possible to produce biochar from seaweed. It will be different than if it's produced from wood or even straw. So it's important to match that type of biochar to a specific application.
Just to go on, sorry.
No, Karen.
I was just going to say, if like there are different grades of biochar that you can produce, is it possible to just use them in applications like building? Like I've heard that you can just put it into like hardcore for roads and things like that. You know, if we could start doing that, then it opens up. You don't have to worry about the quality of it so much. Is that an application that would be something?
Yes, so certainly there will be applications, and I'm sure Saran can speak on that as well. There will be applications that will be less sensitive, and applications that will be more sensitive to the quality of biochar. But I wouldn't say that there is an application that's sort of omnivorous and can take any quality of biochar, because you can really produce all so a very wide range of biochar. For construction materials, one concern could be certain types of metals or sulfur and so contained in the biochar coming from a certain type of feedstock. So all of these will have quality requirements. Road materials or other construction materials might be less sensitive, but still there will be some requirements there as well for biochar quality.
I think it's really about getting the most out of our organic resources. So even these materials have a negative price. There's various things we can do with them, and at the moment we probably don't utilize them very well. So in other words, adding biochar from sewage sludge to land is going to give you more benefits than adding sewage sludge to land, which is what we currently do. But we might be able to find other applications where embedding biochar from sludge into infrastructure projects gives you some other benefits in terms of the performance of the land that's required in that application. And then it becomes becomes more profitable, and that grows the industry faster, I would say. I mean, going back to the algae, I think it's an interesting one. I mean, I think clearly it has some very specific properties, and what I'm interested in is really understanding the size of the biomass resource. So I think we understand biomass on land. What we don't really understand is the limits and the impacts of biomass production offshore at the scale that we're sort of thinking about in terms of onshore biomass. So, the cost of that versus the benefits and the particular properties of the biochar that produced, I think, are an interesting question, which we've have dabbled a bit, but Ondřej's looked at in some more depth, and probably we should explore some more.
Yeah, it looks like something that's really interesting from the point of view that you can just there's no limitations on obviously land competition for resources, and there's no concerns about the water availability. So it's just one of those things. Like I've heard about projects where you can grow it offshore, like in the pelagic ocean, with special kind of apparatus and stuff, and just ideas for what we may do in the future to capture huge amounts of carbon and provide environments that fish can obviously grow in as well or develop in. Just think about it on those kinds of scales, really. So there was a NERT paper, an engineering paper that came out in 2012, and it's talking about tens of gigatons a year on if we maximised it to its full potential. Obviously, you have to factor in dewatering and other factors like that to get the quality of biochar up. But that was the kind of area I was thinking of.
So I would just add one thing to. Sorry, Stuart. Do you want to go ahead?
I was just going to add that in Scotland there was a proposal, I think 2 or 3 years ago, to harvest kelp in the Inner Hebrides, and that failed, not because of the biochar piece or anything like that, but because of the perception of the elected representatives in Parliament that harvesting the kelp would be damaging to the submarine environment. So there are going to be just as many perception and environmental discussions there as there are onshore, I think. So it's not a quick fix slam dunk, but it's something to carry on working on. But of course that shouldn't be a reason for waiting elsewhere. We can do biochar elsewhere on land right away now, for example. And so these are augmenting things we can do, which can provide extra benefits. And as you say, there's a potentially very large source of carbon out there, but we have to find ways of efficiently combine harvesting that in some way.
Yeah, and what I would add to it is also the seaweed has many other uses, so there are a lot of valuable compounds that can be extracted before we convert the rest of it into biochar. So there are synergies between all of these.
And there are many different sorts of seaweed as well.
Yeah.
So there's another question. Are there any problems creating biochar from late-stage disease ash with ash dieback? Are there any solutions to the brittle nature of this wood?
Okay.
Maybe we can go on to another question.
The conditions used would decompose or destroy any disease that's in it, because we are talking about temperatures around 500 degrees and higher. So that there will be no issue. In terms of the structure of the biochar, if the wood already is affected and it's brittle, then the biochar would also be affected by that in terms of the structure. But I can't really say specifically for this. We'll be interested to test it. We have to do that.
So I ask another question. So what are the co-benefits in relation to public health of biochar in reducing is that nitrous oxide or risks in relation to heavy metals, for example?
Shall I do, or you do that? Right.
Yeah, I mean, I think the interaction between biochar and nitrogen in terms of soil and crop nutrient management, and also, I suppose, forest nutrient management in forestry is very important. There's clear interactions between biochar and nitrogen. There's often phosphorus present in biochar. You can choose your feedstock to give you a biochar with a high concentration of phosphorus if you want recycling of phosphorus. But yeah, I think this is important partly because it enables nitrogen to be used better by plants, but also because the nitrous oxide is, or the emission of nitrous oxide from soil is diminished, and that's a very well-established effect. And there's probably 4 underlying mechanisms for this, and really the effect is quite large, even with relatively small amounts of biochar, and it does seem to persist. So I think with regular annual addition of biochar to soils, and I really mean quite small amounts, probably in conjunction with nitrogen fertiliser, this really could have a marked impact on nitrous oxide emission in the same way as additives have been used in other countries. Think about India, really, where fertiliser was co-supplied with pre-coated with neem oil as a way of mitigating N2O. I think we could do something similar in the UK with biochar and have really quite marked effects. In terms of heavy metals, then, as I said, the ash that you get when you burn biomass is present in the biochar, and it is about half of it is soluble and can be leached out fairly readily with water. The other part is quite firmly associated with the structure of the biochar, the carbon of the biochar, and that's really, the composition of that component is pretty much the same as what was present in the biomass. There's rather few metals that are, well, actually, Ondřej say a bit more. Some metals are volatile at pyrolysis temperature or partly volatile, but generally you can predict the metal composition of the ash in the biochar, knowing the composition of the feedstock. So if you start with something that has a very low ash content or low metal content, then the biochar presents no risk as far as I can see in terms of metals. If you start with sewage sludge, then you end up with metals that are less available than they would be in sludge, but the concentration is higher because you reduce the mass and volume of the sludge that you started with.
So in general terms, though, just to flesh that out a bit, I'm keen to emphasize that this is in large measure about authenticating the supply, where the source material and the feedstock for the biochar comes from, because I've talked with people who are very, again, this is the grassroots problem, that you can in principle turn any organic thing into a biochar, and you wouldn't want to turn old car tires into a biochar, even though it may be technologically feasible to pyrolyze them at 500 centigrade. You might end up with more organic tricky compounds and heavy metals than you might want. So for land-based use, for anything to do with growing food or agriculture, then authenticating the supply chain of where the feedstock comes from is important. For if you're using biochar in the foundations of civil engineering or in concrete, then I've got a more open mind on that. But I would still think you probably need to know what you're putting in the ground, even if the intention is that it stays there for a very long time, because you don't want to create contamination hotspots of heavy metals, which would damage us in the future.
Mm-hmm. Okay, I'm going to move on again. How is making biochar different from making charcoal? Is it a temperature burn or eventual use that makes it biochar?
Okay, very good question. In principle, it's not different. The difference comes from the intended purpose for the material. So charcoal used in industrial processes and so on. So ultimately, the carbon that's in it is released back into the atmosphere. In case of biochar, it's created to stay in a solid form and be used for other applications. Also, the range of materials, the feedstock that we can use is much wider for biochar than it is for charcoal because of the different purposes. So for charcoal, we want something that burns nicely and cleanly or can be used in smelting processes and so on. So this will be traditionally produced from woody biomass, from fairly large woody biomass. So it has also the right particle sizes. For biochar, that's much less critical. So biochar can be produced from, we already discussed seaweeds, sewage sludge was mentioned. That can be rice husk, can be all sort of biomass. So as Stuart said, any organic material that contains carbon can be turned into biochar, while that would not really be considered for charcoal. But if you had a sample of biochar and a sample of charcoal next to each other, both of them ground, you really can't tell the difference. There is physically no difference between them. So it's really more about the purpose and perhaps the breadth of the feedstock that can be used or that will be used for that.
Just to dip in there, is that a with the temperature? Is it still an exothermic process that we can like yield heat from for like other uses for municipal heating, for example?
Okay, that's a good question. The pyrolysis process, or the formation of biochar, goes through several different stages. Temperatures. The process.
Sorry, Ondřej, we lost you for a second there. Could you go through that again for us? We lost you for a second then.
Yeah, it's my connection here. The pyrolysis process goes through several different stages, both endothermic and exothermic, but the overall energy balance is such that we can make the process self-sustained and generate some surplus energy. Now that can be in form of heat or electricity, depending again on the scale of the process and the complexity you want to go through. Heat, relatively easy, you just burn the vapors and the gases produced. For electricity, this needs to be cleaned and then used in a combustion engine or a turbine or some other such setup. So again, depending on the scale.
I mean, I suppose the thing to add there is about the moisture content, isn't it? Because obviously we start with something that's quite wet, like sludge, for example. Then energy is required to, well, the water draws some energy or heat energy in order to evaporate off before the pyrolysis starts. It's not completely wasted because you end up with lots of steam that has that energy in it, and then you can recover some of that heat, but it's low-grade heat rather than the sort of high-grade heat that you get from burning the high-quality gases that you would get from dry feedstock, which examples being methane and hydrogen.
Yeah.
But yes, when you look at the whole system, it's net exothermic up to quite a high moisture content. So with biomass, fresh biomass, it's not an issue. It's just with sludges where you've got a high water content that you wouldn't expect to gain any surplus energy, but it's self-sufficient.
So sorry, I'm back. It looks like I dropped out of the call.
Yeah, but we heard enough, I think.
Okay, yeah, I don't know what point because I just suddenly all frozen and I couldn't see anything.
So move on to another question. We have one about the carbon footprint of the whole process because pyrolysis uses a lot of energy. So this must come from sustainable sources to allow a net benefit.
Okay, so again, I think that's partly related to the earlier question. So I wouldn't say that it requires a large amount of energy, and most of it can really be, the process can be self-sustained. So we use the co-products from the pyrolysis process to feed and heat the process itself. So except for the startup, when you do need to provide some additional input, and that can be either in form of gas or liquid fuel, or electricity for the matter, the process can be self-sustained and actually generate some surplus. There are other technologies that would require electricity, such as microwave pyrolysis, in which case, yes, that requires an external source, and that would only really make sense if you have a clean source, so surplus wind or other power supply. But with few exceptions of materials that have a high moisture content and require a lot of drying, the process can be self-sustained, so it doesn't really require a lot of external energy.
Okay, I'll move on to another question. Is there a way or an advantage to creating robust biochar pellets of a large commercial size that could be stored underground safely in the long term?
It depends what you're trying to achieve, doesn't it? So you're trying to get the most value out of the biochar. So I suppose there's different things you can do with biomass, and there's different ways you can store carbon. So I suppose, you know, when we think about biochar relative to some other options for biomass in this area, so combustion with CO2 capture and storage. I mean, you know, different options might be more optimal on different timeframes and in different places, but I think you know, the idea of using biomass simply as a way to store things safely, store carbon safely, seems like a bit of a waste when we know that it can be highly functional and useful in addressing some other issues that we have. So I think we should, yeah, to me it seems like a bit of a wasted opportunity, really.
So it's a bit like putting your money under the mattress rather than investing it in something useful.
So with the different effectiveness at different latitudes and associated climates, what is the potential impact biochar can have in the UK under a changing climate?
Yeah, I mean, I think that is a perception that that biochar only works in the tropics, but I think in a way that's really an artifact of how we've set up scientific studies. So I think the focus on crop yield has led to that conclusion, and also these very large tens of tons per hectare doses of biochar. Clearly, where you've got a yield gap where crops could be yielding a lot more, there's a lot more potential to increase crop yield. In the UK, where we have high crop yields, really what we should be thinking about is productivity and efficiency. So, you know, how much crop we can, well, how much less we can use in order to produce the crop that we get, and how we can diminish the environmental impacts or side effects of that production process. So I think that's the way we're looking at it in the UK, and I don't think really the research that's been done directly informs that sort of idea. So, you know, small regular doses used in conjunction with fertiliser in a way that mitigates the environmental impacts of nitrogen use, for example. So, you know, I think we can be a lot more tactical, and I think the impact on like productivity and efficiency is there. and that's what we should focus on. And I think it will be actually immensely beneficial in the UK, but it won't double our crop yields. At least I should say, so cereal crops is what I'm thinking about. There is clearly potential to increase the yields of horticultural crops, which is sort of an interesting one, but it's sort of a specific topic in a specific sector, but potentially quite important actually. Yeah. High input agriculture.
And we also have some background, some information on if you're planting forestry, for example, you can put a handful of biochar, specified biochar, in with the seedling plant, and you get a better retention rate. So it reduces the death rate of the seedlings. So again, it's an improvement. It's not a it's not a revolutionary transformation, but it's a co-benefit which is useful as well as the soil storage of carbon. So again, it's a portfolio package of many co-benefits, all of which are tending to head in the right direction. It's not doubling the crop yield, as Saran might have put it.
Yeah, and I think we have to be aware of other innovations and things that are already done. So how biochar integrates with other management is sort of really something we could think about quite a lot. In the context of forestry, as Stuart was saying, I mean, where there's the potential to establish the crop faster, so that, lower death rate, but also potentially 2 years off the rotation length. That makes a big difference in terms of the economics of doing forestry. Yep. Both in terms of the timeline and certainly also in terms of the impact on the when the initial carbon cost of establishing forests turns positive with respect to carbon removal. So we've been looking at how these things can work together rather than looking at biochar only in isolation.
Just a quick announcement. Stuart's going to have to go in a second, but Saran and Ondřej have said that they can hang on for a bit longer to try and get through a bit more of our questions. Well, we've been lucky enough to have them. We'll try and hang on to them for as long as we can. So yeah, feel free to carry on going and stay with us with the feed. And obviously, yeah.
So thanks, Ian, and everybody for organising it. I'll just head off quickly. I've got another call straight back to back, but thanks for some good questions from the audience as well, and please do follow up if you want to. Right. Anyway, over to Saran and Ondřej.
Thank you.
Okay, so I'll read out another question. Which countries are the real world leaders on biochar, and what can we learn from their approach to developing its use?
I don't know. I think the UK is on that list actually. I think because we've been working on it for a long time, and I think actually we've been quite strategic. And I think some of the sort of the current activities around deployment, I think it is driven by to a large extent, I think by the government's commitment to net zero and the time frame. I think the UK can become a leader. I don't think it is at the moment, but I think it can become a leader. I think in other countries around Europe, and actually Ondřej might have a different or similar list. So other countries in Europe where there is commercial production of biochar, it's interesting because I think that's we can actually benefit from that and learn from it. But I'm not sure that they've cracked it in terms of getting on a track to a very large number. So they've got commercial quite quickly, but I don't know if they've really got the roadmap to 1 million tonnes a year. Whereas I think in the UK, I think that pathway is actually quite clear, and I really think it will happen. The US is sort of interesting because it's different depending on where you are. Things are organised and regulated very differently, and also financed very differently. And it's a bit hard to tell. It's quite patchy, but obviously it's a very big country and there's a lot of capital. As the carbon removals market is growing so fast, there's going to be a rush to invest, I think, and it's sort of almost on top of us. And we really need to be in a position to create good, I say projects, but I really mean markets for biochar, biomass for use in particular, biomass to use in producing biochar for particular uses. I think we can be a leader, but China, I suppose, is probably organised very differently, and there's very many examples in China where biochar is already being used in many different ways at a range of scales. I think, Ondřej, do you want to add to that?
Yeah, no, I think I agree with Saran, what he said. There are various examples across Europe, in China as well. I think it's in particular in China, they've been very quick moving from sort of the research phase into initial industrial actual applications of production of biochar and applications. But I agree. I think UK has the potential to become a leader because of the strategic position and the strategic thinking behind the commercialization of biochar.
I'll move on to another question. Is a library of biochar characteristics being developed for different feedstocks to help different users understand which type they need? Biochar from bracken?
Okay, so I can start on that one. So, well, we do have an in-house database, and it's actually available sort of beyond just our group or our center, where we collect information on properties of biochar. We know the materials they were produced from and the conditions. In terms of sort of a holistic understanding of how all these things link together and having some sort of a predictive capability, I think we are making good inroads on that, but there isn't yet a sort of a single recipe how to prescribe one thing to all the way from the feedstock to the conversion all the way to the application. Although there are some clear indicators of what makes it better and what makes it less suitable. Regarding specifically biochar from bracken, again, it's not something we've done a lot. We've done, I think, few samples of it. Again, just like most materials, it is possible. It's difficult to tell whether it's suitable for a particular application that the person asking the question has in mind. But yeah, we can produce just by changing the conditions or using various additives, we can form various different types of biochar. So we can make suitable biochar for many applications from it.
Yeah, I think that's right. It's partly what you start with, it's partly how you convert it, it's partly the sort of the socioeconomic context. We always had that sort of triangle really so that we could gather the sort of generic knowledge that enables us to help with the specification of particular biochars for particular uses. So I think we have, I think that knowledge is pretty sound now, but I think it's very much a case where we could where we have knowledge that is then validated in a test. I don't think we don't know as much about biochar as we do about, say, chemical fertiliser products, for example, which are incredibly well specified, and decision support models already exist. We're not really at that stage with biochar, but we know, broadly speaking, which types of biochar will provide which function. And I think if we had the information on the composition of the bracken, I'm sure we could come up with a suggestion about how it might be made into biochar for a particular use. I think that's not really a problem.
Okay, I'll move on to another question. Is a biochar code similar to tree code by Forestry Commission being created?
I guess this is for this is in terms of carbon accounting, I think, isn't it?
Mm-hmm.
Yeah, yeah. I mean, there's a number that are around at the moment that are, I suppose, in a way, competing. And some years ago, when the International Biochar Initiative came up with a very detailed accounting protocol and submitted it to the American Carbon Registry, it's a bit like gold standard, really. It was unsuccessful. It was a bit too early, and markets weren't looking so hard for removals technology because there were a lot of other offsetting projects around. But I think now the market for carbon removal is growing. And I think Puro Earth, I think, is probably the sort of example that, well, I think people have been looking quite closely at Puro Earth because NASDAQ have now bought it, as far as I can tell. Biochar has quite an important role in their model because it's really one of the few removals technology beyond planting trees that anyone can really do at the current time. So although there's rather few projects, the value of biochar in the carbon markets has escalated because it's a removal and because it's one that we can actually do at the current time, which, you know, for all the potential of CCS and bioenergy with CCS, although we know how to do it, it's quite hard to get going with it because of the scale, the minimum scale at which CCS projects operate.
We do have another question about, can you say more about the scale of the plant? So the minimum scale for viability and the maximum potential of the scale given the average availability of feed?
Okay, so well, there really isn't a minimum size. You can really do it on a very, very small scale, and we've done tests. The readers or those listening here might have heard of cook stoves that are used in developing countries, and that's really probably the smallest scale you can produce biochar on, which is really a few hundred grams of biochar per batch. But for anything sort of at least farm scale, for farm size, hundreds of kilos or a few tons per day would be a suitable scale, and there are already existing units you can buy on the market for production of biochar at that sort of rate. As for the largest scale, that really will then become a feedstock supply sort of dependent, how much you can bring in within a reasonable radius. So we start to sort of have to address the same questions as bioenergy plants that need to be supplying biomass from quite a wide range. The biggest plant I'm aware of is operating at a scale of around 100,000 tons per year. So that's probably as large as you go. I mean, there is technologically you can go bigger than that, but I think that you really sort of start hitting the logistical problems of supplying biomass. And then also, because this is a two-way system, you not only need to bring biomass in, you also need to distribute the biochar. So you need to have an outlet for the biochar. You need to be distributing it to the different applications within that range.
Yeah, I mean, I suppose it's the viable word, isn't it? That's sort of critical here. So yeah, depending on what you're willing to pay, then any scale is, depending on what the price is that you're willing to pay, then any scale is viable, because you can do pyrolysis at any scale. The viable scale in the real world varies according to your situation. I think where you've got a point source of biomass, it is different than where you're trying to aggregate biomass over a wider catchment and bringing it specifically for the purpose of pyrolysis and then redistributing it. So, you know, we have looked a lot at timber processing, for example, where you've clearly got a lot of biomass going through a site, and that's an obvious place to put a pyrolysis facility. And I suppose you say, you know, with sewage sludge, then large water treatment works. You can say the same. We have examples from straw burning power stations, not terribly successful in a way, but we know the impacts that's had on the land. We know the contribution it's made in terms of energy generation. I think what's quite an interesting one to reference with biochar, because actually energy is sort of cheap, and you've got this downward pressure on prices because renewables are getting so cheap. That actually biochar starts to look very attractive, because sort of whatever you do with it, it's got to be worth more than energy. So it starts to look like the right thing to do with biomass, because it's a more valuable product if you're using it correctly. And if it's going back into the land, then that's good for the land, not bad for the land. So I think there's lots of possibilities to be operating at large scale. And of course, it's it's not really a one-person operation producing biochar, but clearly in this part of the world where labour costs are high, capital is cheap, large scale is always going to be or larger scale, I should say, is always going to be the right way to go as far as I can see commercially.
Are there any good examples of small-scale biochar production by a farmer or woodland collectives, for example?
So there are not so much in the UK yet, but Saran already mentioned examples in Europe. So there are quite a few new installations running for the past several years in Scandinavia, especially in Sweden, but also elsewhere in Europe, so Switzerland and Austria. and so on. So there are good examples of those. And as I said, there are already units on the market that the farmer can buy, have it installed, and after some initial training can be operated on the farm.
Yeah, I suppose in terms of, when we look at the economics of this, so we think sort of the break-even cost of producing biochar from something like straw, which has a sort of defined market price that's actually quite high. It's going to be hundreds of pounds a ton. So although farmers can do it on their farm, they have, I presume that they need to be using it in a way that justifies that sort of price. So I think it has to be integrated with something that's very expensive, like fertiliser. Otherwise, it might be difficult to justify. There, I suppose I'm thinking about arable agriculture, but when we think about livestock agriculture, the economics are very different, and I think we've probably underestimated the potential for the use of biochar in the livestock production system, because animals are very valuable. And yeah, I think it's a more complicated system, but ultimately it might be a very important one.
Okay, I'll move on to another question. Are any trials planned for UK biochar using wood harvest from Caucus or other sustainably managed woodlands? Are any landowner networks being approached?
Yeah, so I suppose, I mean, in terms of sort of short rotation coppicing, so dedicated crops, I'm aware that, under this sort of recent set of 24 feasibility studies funded by Bayes, that there is a short rotation coppice biochar project. So that's creating a specific type of land use system for producing a secure supply of primary biomass for use in biochar production. Not sure if that was necessarily the sort of the context that was being thought about there. These are very commercial, and they involve large areas of land, and they're linking the production of the biomass to the processing of the biomass to the use of the biochar. And I think that's actually at the moment the only way you can make this work, because otherwise the commercial risk is too high. So in other words, you wouldn't create a biochar plant without knowing where your feedstock was going to be coming from, or who was going to buy the biochar. So these sort of vertically integrated systems, I think, are the solution, as it were. But I mean, that doesn't have to be a single company production system. It can be a collective of landowners, but I'm not aware of any sort of collective that's come forward and proposed to utilise that, or to create a supply of biomass that would be at a scale relevant to a biochar project. But I think that's got possibilities.
Just to dip in, if people were thinking of projects like that, do you reckon you guys would be the best people to come to kind of field questions on that kind of thing, or are there other places that you would point them to?
Yeah, I mean, I think we've got our ear to the ground. We're academic, but I think sometimes we do sort of filter a lot of the information that's going around in an academic sense. I'd like to think we're useful, and certainly willing to convey what we know. So yeah, I think so. Yes.
Just one other thing. Do you think the fact that biochar is completely stable, basically, and we could probably store it in lots and lots of places, and we won't have to worry about it leaking out of any geology or any of those kind of things. Do you think it's basically a battle against what's happening with the oil and gas industry, trying to kind of dislodge their kind of power base in a way, or just wait for this to become so beneficial or so obviously a good solution before biochar really starts to work at scale in areas of just cold carbon capture and storage?
I don't think I think the oil companies, I presume, that's the writing's on the wall, really, isn't it? The other sources of energy are becoming cheaper, and the requirement to, reduce net emissions to zero means, this is difficult. I mean, for the residual fossil fuel industry, I think there'll be trying to buy removals from anyone who's willing to sell them to them. So I think they become part of the driver for removals, which is obviously potentially controversial because it might seem as a way to be perpetuating carbon emissions elsewhere. But actually, given that there's some recalcitrant sort of uses of fossil fuels which are going to take longer to dislodge, and I think about aviation, maybe it's actually necessary. So no, I think it's just actually more on I think it's leadership in government, and I think proaction from regulators really, because I think understandably in a way we're very reactive with in a regulatory sense. If you want to put something on the land, you go through the process of getting permission to do it, but government isn't pushing for the regulation that permits the use of biochar. That has to be driven by industry, and it's a process that takes some time. So I think that's the rate limiting step at the moment, really. And obviously the market's got to develop, but it's in a sort of a slightly vicious circle between regulation and commercial appetite.
Just quickly, are you seeing any movement in the regulatory situation at the moment on biochar, or any significant movement?
Yes, well, I think because there's more movement commercially, it is pushing. It is going to force the issue with regulators, which actually I suppose is what regulators have been waiting for. Because, as I said, it's reactive. So once there's a clamour, which is what it's going to become, for a position on this technology, there's the necessity to address it. So I think it's beginning, just from our own experiences in some of these feasibility studies. But yeah, I think it's going to become a much. I suppose regulators could be a bit more, probably benefit from seeing this coming. So I think it is going to become, a bit of a demand, on time within the regulatory regime than it has been.
Thank you.
Okay, I'll read another question. Can biochar be used for treating water before recharge to aquifers? Will it remove contaminants?
Yes, so biochar can be used, and there are
Connection issue
that
found.
could be. Sorry, can you hear me?
We lost you there, Ondřej.
Is it okay now?
Mm-hmm, yep.
Yes.
Okay, good. Yeah. So I'll start from the beginning. So yes, biochar can be used for treating of water. That can be drinking water. It can be wastewater, so effluents, for removal of different contaminants. So it can be anything from heavy metals. It can be organic pollution. It can be emerging contaminants. So all sort of things. Not necessarily always the same type of biochar. So again, it comes really down to selecting the right type, or designing the right type of biochar for the particular contaminant or set of contaminants you want to be removing. So it definitely has its role in water treatment, and then the question is also, what can you do with biochar after the use?
Just give him a couple more seconds. It seems that when I talk, his connection starts to reconnect.
Yeah, I think what Ondřej is saying is that, clearly you've got this potential to remove things with biochar, but what you've then removed onto the biochar can present some difficulties, because, if you didn't want it in the water, it's now on the biochar. So that may compromise what you want to do with the biochar, unless you have some way of removing it from the biochar. So, where, in the activated carbon industry, for example, where organic contaminants removed onto activated carbon can be removed by reprocessing the activated carbon without affecting the carbon itself. With metals, I think it's a bit more difficult because they are absorbed and not can't be volatilized. Ondřej, sorry, you're back.
Yeah, I'm back. Apologies for this. It's probably time for me to go. Losing signal all the time. Anyway, so I've got Saran covered that option. I think I hopefully answered the question.
Yeah, it did. I think after that as well, I think we're going to wrap it up now. So I just want to thank everyone for taking the time out today to come to this event. The new cross-government climate hub has recently been launched. This is an online space to connect all public and civil sector workers to build ambition in government on addressing climate and the biodiversity crisis. The public sector is hugely diverse in the type of work and the experience of people, but it lacks connectivity. The new hub aims to provide a connectivity and collaboration between the different climate groups across all public sector. You can access our resources through the link tree in your pre-event email. And here you can also find a link to the sign-up page, which will guide you through how to use our hub. We will also be sending out a post-event email with all these details again, including links to our Twitter, LinkedIn and Facebook pages. So please make sure to follow us on these platforms. This event will be available on YouTube for you to share afterwards, and please let anyone know about us. Anyone working in the public sector is welcome to join us in the Collective for Climate Action and also on the Cross-Government Climate Hub. And thank you so much to Saran, Ondřej, and also to Stuart, even though he's gone, for taking the time to speak to us. I know I've learned so much, and all our listeners seem to be enjoying it too. So thank you so much for coming.
Yeah, thank you very much for the initiative. I think it's great that you have this hub and this connectivity, creating this connectivity. And yeah, I really appreciated the questions. I think they were great. Clearly, interested audience. And yeah, for those who are interested in have questions that pop up after this session, please send them to us if you think we might be able to help or comment or point you in the direction of someone else who can.
Yeah, no, I completely agree. And thank you for the opportunity.
Thanks very much for coming, and thanks, guys.
Thank you all.
Thank you.
Bye.
Thank you. Bye.
Bye.